This call is now being recorded. This call is now taking notes.
All right, so moving forward to the next topics, we already derived the general mole balance of the systems with any volume of V. So from the last video, we already seen that the in minus out plus the generation is equivalent to the accumulations. So this we derived already from the last video. If we have any volume, so if have the inlets and it has an outlets, it has an outlet, sorry. So the inlet is Fj naught with an outlet of Fj, and this is the volume V. So in that, we already derived this formula with which the mass in is equivalent to the mass out. So now we're moving forward to the type of the processes and the reactors that we will learn in the chemical engineering knowledge. We know that there is two types of the processes. One is the batch process, and the second one is the continuous process. So what is meant by the batch processes? The batch processes, we can use the batch reactors. So what is meant by batch reactors? So assuming you are making a Milo, so I use this example. So you are making a Milo, you have a cup, and you put the Milo powder, and you add the waters, and you add the sugars, etc. So after that, you make a cup of the Milo. So it's finished. So you need to wash the cup again, and you make another Milo, right? So you cannot continuously make Milo when you want to drink it. So this is we known as a batch reactor. So each time you make Milo, you can ensure that, okay, I want to put 3 teaspoons of sugar. So next time we also put 3 teaspoons of sugar. So this is how we known as batch reactors. And we have the semi-batch reactors. And through the continuous process, we have the continuous stir tank reactors. Continuous stir tank reactors. Stir tank reactors. So this is known as the CSDR. CSDR is something like of containers. You have the stirrer, you have the agitations. So it continuous feed and continuous outlet. So in this case, we cannot control the quantity because each time the feed is different. So let's say I pump in, you make a Milo with an inlet and outlets. Here is the inlet and here is the outlet. You continuous feed the Milo powders and you continuous add the waters. So each type of the Milo will be different taste because you're adding some uncertainties of the feed conditions. So this is the uses of the continuous stir tank reactors. And we also have the tubular reactors, in which it is known as a plug flow reactor as well, which is PFR. And finally, we have the packed bed reactor. Packed bed reactors. So packed bed reactor is known as PBR as well because we know that it has a membranes or it has a catalyst deposited on wall of the surface. So it's generally a continuous process because we continue feed and continue outlets. So we need to have a feed in and feed out. So this is known as the tubular bed reactor. So after we understand all the processes and the reactors in chemical engineering syllabus, so now we move forward to the first one, which is the batch reactors. So what is batch reactors? So we see some of the characteristics in which first the reactants are placed in the reactors. Okay, this is something is very normal because we know that we need to add some Milo powder. As I said just now, we have to add Milo powder, we have to add water, then we starting to stir. So it is not stir over time. So we need to stir at certain point only, and we can manage it batch by batch. So the reaction is allowed to process for some amount of time, means that you are stirring it for some amount of time. Let's say you're making a Milo. So closed system, what is mean by closed system? Closed system means there is no addition of reactants or removal of products during the reactions. It means like that you are making a cup of Milo, then I adding the Milo powder and I adding the waters. So then you're starting to stir using a spoon, using a teaspoon. So you stir it. In the middle of your stirring, you didn't add the Milo powder really. So you didn't add the water, continuous adding. So it's just like batch by batch. So you're adding the Milo powder once and adding the water once, and you start to stir and it become a cup of Milo. So you didn't add something like Milo, you didn't add sugars during the reactions. So it is an unsteady state conditions, which means because in industrial standard, we cannot assume like it is a very steady state because steady state is just like for the lower assumptions. In general, we cannot use steady state conditions. So next one is the ideal batch reactor assumptions. What is mean by ideal batch reactor? So ideal batch reactor means that the vessel is perfectly mixed. perfectly mixed. All right. So here is the perfectly mixed. Mixing means also it is partially constant. All right. So moving forward to it means like what we explained in the last videos, the spatially constant or spatially uniform means that we have the CSDR here. So at point A and point B is here is the batch reactor. So at point A and point B are definitely the same. So they have the same characteristics. So that means we no need to imply the very complicated stuff in here. So we are just assume A and B is the same. So moving forward, we need to define the batch reactor has their characteristic, phases, applications, advantages, and also these disadvantages. So what is their characteristics? So first one, they are the closed systems, as I mentioned just now. And second, the assumptions. The key assumptions are it has the constant density and it has the well mix. So what is mean by well mix? Well mix means that density is constant and the temperature are spatially uniform. So when XM asks you to give some assumption, you can give these assumptions that this is constant densities and it is well mixed, which means the density and the temperature are spatially uniform. So what is the phases? It is usually we use it for the gases and also for the liquid phase reactions. And what is the applications? So it is used for the small scale operation. And when you want to test a new procedures, testing a new processes. So what is something like this? Let's say pharmaceutical. You want to produce medicine that is used for the cancer. So you cannot testing like, okay, I continuous feed this, I continuous feed that, and produce the product continuously because it will be very expensive. So we are using to manufacture some expensive products because it requires a long reaction time and we need to obtain the kinetic data for scaling up. All right. So what is the advantages? We can see it has the high combustion per unit volume for one pass. What does it mean by high conversions? So high conversion is means by when we feed some things, like just now I mentioned the Milo example, you are making a cup of Milo. So in this conversion, because you stir it, stir it using your teaspoon because you're adding a fixed amount of Milo, you're mixing a fixed amount of water and you mix it well. So you can ensure the Milo product you get, that is a Milo liquid, is sufficiently very high. It's very high conversion. It's not more Milo powder anymore. So that's why we say it is high conversion per unit volume for one pass. Unlike the continuous process, you continuous feed the Milo and continuous feed the water. So it is most of uncertainty is there because we cannot ensure every batch product is the same. So in batch reactors, so we can ensure the high conversion per unit volume because we fix the amount. We mix and we mix well, mix for a long time, and this is how its advantage come through. And the second advantage is it has flexibility of operations. What does it mean by flexibilities? So flexibility is very important. So let's say in this case, in the first, let's say if today is Monday, I want to drink a Milo that is less sweet. So I only add 1 teaspoon of the sugar. And second day, I feel like, oh, I need more sugar. So I add 2 teaspoons of sugar. So definitely it has the flexibility because we are not continuous feeding the feed. So we can control it. So here is the flexibility of the operation meaning. So what is the disadvantage of the batch reactor? Of course, just now we can see it has the high operational cost. Why? Because we can't produce the same products every time. Production is very slow because we need to monitor it batch by batch. And first, the product quality might vary varies because we didn't feed it as continuous. Even though sometimes we're getting a very good product, you can't ensure the Milo is same taste with the previous, right? So we have the various product qualities and also long reaction time. So here is the three disadvantages of the batch reactors. So moving forward to what we learned in the previous video is the mole balance. So how we derive the mole balance for the batch reactors. So if you watch back my previous video, I already derived the formula Fj naught minus Fj plus. This is the generation equivalence to the accumulations. So from here, the general design equation, how we derive this formula into the equation that is suitable for the batch reactors. So in this case, we need to understand the characteristic of the batch reactor. First, we just now already mentioned it has the no continuous feed, and it is a closed systems. And finally, we can decide that Fj naught is equivalent to the Fj, which means it is zero because it is a closed system. We didn't feed it, so it's like a cup of Milo. You feed it in the initially at time of zero, you add the Milo powder, you add the coffee powder, let's say coffee powder, you're making a coffee powder and you are adding the water. So you didn't add it during the reaction. So the Fj naught is equal to the Fj is equivalent to zero. So in this condition, we can cancel out these two terms. So it becomes integrate of Ra dV. I'm sorry, it's supposed to be Rj. Rj dV equivalent to dNj dt. So how we do this? Because we already assume it is perfectly mixed, hence partially uniform, which means the density is constant. Hence, we can, if the since you know that rho equals to rho equals to mv, right? Rho equals to mv. This is the mass, this is the volume. So in terms of that, dv is equivalent to zero because there is no change of the density. So rho dv is, I'm sorry. So, sorry. Rho equals to mass over volume. So in case of volume, this didn't change because the mass is the phase. So volume is the phase. So now the volume, since we are saying the volume is a constant, and hence dV will be equivalent to zero. Since the density change is zero, so the mass is unchanged, so the volume is unchanged as well. So in this case, Rj dV will be equivalent to Rjv, while this volume is the volume of the batch reactors. So in this case, we already identify how we derive this formula. So from here, we can get Rjv is equivalent to dNj dt. Okay, so now we further simplify from this equation, we make it as 1. So from equation 1, how we further improve it? So we just play around with value. So dnj, we put the rjv over here, so it becomes rjv and equivalent to the dt, right? So we move the dt here and we change the place. So let's starting from the integral now. So when t equivalent to 0, when we adding both integral here, when t equivalent to 0, you can say the NA, NJ is equivalent to NJ naught, right? Because we have the system at time equal to 0, you just adding the amount of the Milo powder, so it's a NJ naught. So J is a species J. It can be anything. It has to be your feed. So NJ naught is your at time equals to 0. So in this case, at a T, and when, sorry, I put here. So when T is equivalent to T, so NJ will be equivalent to NJ1. And hence, you will get these formulas from NA naught to, I'm sorry, NJ naught to NJ1, dNJ over RAV, RJV. So it's equivalent to 0 T dt. And hence, you will get T minus 0, so here is T, and you will get this value, NJ naught, NJ1, dNJ, RJV. So, and we further improve that because we know that as we derive, so now we have these formulas and how we're going to do it because we know that Rj is the rate of disappearance of the reactants. As I said, because we are adding a Milo powder, we have the Milo powder here. right? So keep when we have the Milo powder initially, over the time, the Milo powder will decrease, right? It will produce a fresh Milo. So overall, it will decrease and decrease, decrease. So it is a reactant. So we must make this term as the negative. So it is a rate of disappearance. So at the end, we will derive a formula of T, and this one we just times with we just multiply the terms with a negative one over negative one, and it will be same. So you will change your NG not NG1. You see this is clearly see here and here. We are changing the terms because we want to make this term negative. So it will become something like this dNG over negative RGV. So this is the general design equations of the batch reactor. So here is the ideal batch reactor design equations. So this design equation we can use for any questions of the as long as a batch reactor, we can use this equation to solve it. So it's very easy. The question will be given the NJ naught, given the NJ1, so you just substitute it integration using your calculators. So you will get the answer very easily. So I believe here is all the video. So in the next video, I will derive on the continuous tank reactor, which is the CSTR, and I hope to see you in the next video. Thank you so much.